Okay, vector functions as position vectors. Exercise 5A and 5B you'll be able to do after this. We'll just look at the 5A stuff today. So here's the first part, using vectors to describe motion. So you'll see typically this is where we're going to break things up into parameters. And the parameter will be for position vectors, so vectors as a function of time. The parameter will obviously be time, and it will be measured in something seconds, hours, minutes, days, whatever. So just keep that in mind. I is in the x direction, j is in the y direction, k is in the z direction if we're considering three-dimensional. But again, mostly it ends up being two-dimensional. And if we need to consider a third dimension, often we'll produce two vectors to represent that, to simplify things a little bit, but maybe not. R is also a fairly common position vector notation. So you can call it D or X or P for position, but R seems to come up a lot, so I'll be using R typically. And to write a vector as a position vector with the parameter time, we have an I component and a j component, and both of them will be represented in terms of time. So that way we can substitute in 2 seconds, for example, and it will tell us where this thing is after 2 seconds as an I and j component form situation. It represents the location of a thing at some time, and the thing is often a particle in the textbook, but it could be anything. So go with that. Obviously, if it's a particle, that reduces the assumptions and the issues involved. But if it's a football or a person or I don't know, whatever else it could be, there's air resistance, drag, all that kind of stuff that comes in. So this would be called parametric or component form. And here's our first example. So we're going to eventually draw the position vector here. And I've kept it fairly simple in the first case, and then we'll build from here. So in example 1, given RT, which is our position vector notation, equals 2ti plus 3 minus tj, complete this table. So the table represents the position of the vector at 6 different moments, along 6 different time periods. And so when time is 0, I just go straight to that function up there, and I can work out r of 0 is equal to 2 times 0 I plus 3 minus 0 j, and that ends up being the I component is at 0 and the j component is at 3. So we've just substituted in 0, I got that. Hopefully you can see that if I substitute in t equals 1, then r of 1 equals 2 times 1i, which is 2i, plus 3 minus 1j, which is 2j. So I get 2, 2. The x component just doubles every time, or not doubles every time, it's just 2 times the time, 2t. So I get 0, 2, 4, 6, 8, 10. The y component is 3 minus the time. So that becomes 1, 0, negative 1, negative 2. And I can now plot that to represent the position of this particle over time. And you'll be able to garner from that where it is at 1.5 seconds or 1.6 or something. So if I plot this, 0, 3 is out here somewhere. That's wrong. 0, 3 is there. 2, 2 is here. 4, 1 is here. 6, 0 is here. 8, negative 1 is here. And 10, negative 2 is there. So what type of function is it? This particle is following a linear path. Does that make sense? Now we have this our scale here is x and y. There's no representation for time. So as soon as I sketch that, I don't know what time it is where. That's why this is so powerful. This form up here gives me the position as an x, y coordinate and at a certain time. As soon as I sketch it, I've lost that information. I don't know anything about the time anymore. So that's something that's important to keep in mind. This is representing 3 different variables, that single position vector at the top there. Now I'd like to know if you can determine the linear function y equals f of x of this function here. So that's y equals f of x. Can everybody determine what that function is? What is it? Just sub in some points. Negative 2x plus 3.
Negative 1 over 3. No, negative 1 over 2. Yeah.
So negative a half x. Everybody happy with that? It has a y-intercept of 3, and when you go along 2, you go down 1, so it's got a gradient of negative a half. Yep? But now that's, we're lucky. This is a linear function. The point I want to make here is that this might not be linear. This could be a whole range of different things. How would we go about developing this function without just using our understanding of linear functions here? And I'm going to show you in this instance, but you'll obviously need to be able to build these things yourself. So this will be my little OR clause. It is going to take longer this time, by the way, than it did to just develop that function. Although to be fair, you threw about 4 or 5 different answers at me. So RT was equal to 2TI plus 3 minus TJ. Hopefully, you're able to see from that that X is equal to 2T and Y is equal to 3 minus T. I'll call that 1 and I'll call that 2. Now, if we know that Y is equal to, X is equal to 2 times T, hopefully you can see that in number 1, T equals a half X. Are we happy with that? Now I can remove the T. This is basically simultaneous equations. There are 3 unknowns though, so I'll never be able to solve it. And that makes sense because there's not a solution. There's an infinite number of solutions along that linear line. But I can get Y in terms of X by eliminating the T. So I put this into equation number 2, and I get Y equals 3 minus a half X. Or Y equals negative a half X plus 3, which is what we got. The point here is, yes, it's linear, yes, we can work out linear quite easily, but if it's quadratic or circular, they're the 2 main ones you're going to talk about in this topic. So circular motion or quadratic motion, which is projectile motion. If it's either of those, we can get here, develop an X representation, a Y representation, and then eliminate the T to get an overall representation of the position vector graphically. And it's going to look the same every time. We're going to start with that every time and then do some rearranging to get this. Any questions on that? I think that's what I said here. In the example above, could you determine the answer to C without A or B? Explore. We did it. I know what that is. Leave my smiley face alone. And so if there's no questions, I don't think there is. Let's consider another example. Example 2, and then I'll do example 3, then I'll stop. Example 2. Determine the Cartesian equation for the vector RT equals sine Ti plus cos Tj. So at the moment it's a parametric or component form, so it's in parametric form. We want to determine the Cartesian equation, which means we have x against y to represent that position vector. So for A, we have RT is equal to sine of Ti plus cos of Tj. So what's the first step I'm going to take here? So x equals sine t and y equals cos t. Now, how am I going to eliminate t? T equals inverse sine x, and then therefore y equals cos of inverse sine of x. Who thinks that sounds fun? What if I told you there's a better way? You can believe me. But it does involve a small trick that you'll know. Very soon you'll know it and you'll be very comfortable with it and you'll be able to use it easily. And it's a little bit obvious, but it's hard to pick up to start with. So I'm going to leave it with you for 30 seconds. Can anybody come up with a way of eliminating t here? And I'll give you a bit of an bit of a clue. It's to do with trig identities. Go. So say that again. So if I go 1 squared, I get x squared equals sine squared t, and 2 squared, I get y squared equals cos squared t, and then if I add those two together, I get x squared plus y squared equals sine squared t plus cos squared t, and that means that x squared plus y squared equals 1. Happy with that? And what's this shape?
Circle.
It's a circle. That's a circle function. Okay, math methods, term 1 last year. Circle function. Oh, this year, sorry. Circle function just there. So this is my despair face. I like this one. Anyway, I'm recording. Chit chat. Okay, question B. Anybody got any ideas how we might do question B? Shall we start with have any what's in it? Not these documents. Yep, I'll be fixing it. Okay, so part B, the trick here is that if you square both sides, you do get a slight problem. You end up with 4 sine squared t and cos squared t. You have two options. Dylan, you got an answer to one of them? Oh, whoa. Well, you won't eliminate the t, you'll just end up with sine 2t. You'll end up with xy equals sine 2t, which is probably more complex than we need. Well, how about we square them anyway? Okay, now what can I do here to fix the problem that I have? What about if I change this to 4y squared, 4 cos squared t, and then add them together, and I get x squared plus 4y squared equals 4 sine squared t plus cos squared t? No, this is not a question that has just an answer at the end. This is the whole function on it. Yeah. What shape is this, by the way? No, it's not a triangle. It's a what size? Circle? No, not a circle. It's not a semicircle. An oval, yeah, it's an ellipse. So you'll be dealing with questions, if you've got a coefficient of x squared or y squared that differ, then you're now dealing with an ellipse. Remember, a circle is a special type of ellipse. So this will be an ellipse. You can draw it on Desmos if you want to. Now I've got a few different, I just want to show you all the varieties that you might get. So question C, the functions, this is actually easier, sine squared plus cos squared. So you get RT equals sine squared t plus cos squared t. That's I and that's J. So for question C, I start by breaking it up into x equals sine squared t and y equals cos squared t. Does anybody know what type of function we're going to get this time? Linear, indeed. Okay, I don't have to square both sides this time. So when I add them, I get x plus y equals sine squared t plus cos squared t, which gives me x plus y equals 1, y equals -1 plus x, or whatever version. So this is another representation of a linear function, which hopefully should trigger in your mind the fact that if you have a position vector, so the actual Cartesian form, and you want to make it in the parametric form, there is not a unique answer. There are multiple ways you could do that. So just keep that in mind as well. D, last one. RT, there is a unique answer if you know information about the time, by the way. If you don't know information about the time, like you don't care where on the circle the object starts and how quickly it goes around a circle or whatever, then there's not a unique answer. The last one was state the domain and range of each motion vector above. Why is it so hard? It's not. It's easy. You'll get that. Okay, so the first one is a circle, and what's the domain and range? So it can be written like that, or it can be written as -1 to 1, like that. Curly brackets because -1 and 1 are included. And the range is the same because it's a circle. And what about the second one? B. Okay, what are the possible y values? Sorry? So if y is 0, what can x be? I know you did. Did you know why? Okay, so gentleman over the back there, there's our domain and range to the second one. We have some slight differences for ellipses that you'll have to deal with. And the last one, what's the domain and range? What possible x values exist? So any values, yeah? Okay, that's it. And example 3, very quickly, and then I'll just quickly show you the summary, and then we'll talk about the rest of the stuff tomorrow. Write a motion vector, y equals x cubed. Write the motion vector, so the motion graph, graph was right, function. In component form, is your solution unique? We know the solution is not unique now. So can you get that into component form? Can somebody give me a vector that is parametric in terms of t that actually represents the function y equals x cubed? The answer will start with this, RT. T cubed. So y equals x cubed, y equals 0 the whole time? No, be careful there. Does that work?
Yes.
So this would lead to this. X equals t cubed, y equals t, and if y equals t, I can substitute t out and put y into the x function, giving me x equals y cubed. Let's make that the cube. So that means that, see how this is, y is depending on x, whatever x is, y is that cubed. Whatever x is, y is that cubed. Okay, now, yeah?
Y equals K, so you sub in the Y.
Okay, this is one possible solution. There are multiple others. I'm going to leave it with you to see if you can come up with another. I might just change this over. Yx cubed. And we'll do that. So just a quick summary. T is the time, it's our parameter. RT is the position at a given time. It's as written as a vector. RT equals FTI plus GTJ, or possibly FTI plus GTJ plus HTK. It could be three-dimensional, but we won't play with that to start with. And this leads to Cartesian form y equals f of x. Getting from here to here, component to Cartesian form, needs to be something that becomes pretty trivial for you in the basic form. So if I give you one that ends up being a circle, ellipse, linear, quadratic, that's pretty easy, or actually probably polynomial. Anything else, it can be a bit harder. And the main types are this. See how that's linear and linear? It will lead to linear motion. So this is my summary. See how this is linear and quadratic? It will lead to parabolic motion, quadratic motion. Periodic and periodic will lead to circular motion. If you've got linear and cubic, it will lead to cubic motion. If you've got quadratic and hexic, so if it's t squared and t to the power 6, then that will probably lead to cubic motion again. So see how that t squared cubed becomes t to the power 6? That's the relationship that will work. And now this is really common. We'll use this a lot. So the number 2, this one here is projectile. And this one here is circular motion, simple harmonic, or circular motion, which we will cover. And yay, that's the end of my lesson. Thanks.